There are certain problems that you come across which don't have closed solutions. They don't seem to have any nice, neat answer. A lot of times when you go to infinite decimals, they don't have nice answers. The most famous of all integrals that you can't come up with an answer for looks like this. E to the x squared dx. There's no way to integrate this. There's no closed form solution, as they say. However, you could rewrite that as the summation k equals 0 to infinity x to the 2k over just k factorial. And then what I could do is integrate this each piece at a time. Like then you would have, I'd put the summation outside, k equals 0 to infinity, integrate. I could even take the 1 over k factorial up front, and I would have x to the 2k dx, and everybody knows what that is. We have k equals 0 to infinity, 1 over k factorial times x to the 2k plus 1 all over 2k plus 1. I'll stop right there, plus a constant if we need to have it. But the point I'm making is that this is an impossible problem unless you go to infinite series. Well, that's exactly what we're going to be looking at here. If you remember what a power series looks like, they were infinite series, but they were equal to functions. And they look something like this. K equals 0 to infinity, a sub k x to the k power. So this is the general format for a power series. And all those questions that you have about the interval of convergence and all that kind of stuff come into play here, but not so obviously. We're going to mostly just manipulate these things and not really appeal to a lot of the details on them. But you should know, typically when the series converges, it converges about some number, let's call it x equal to a, and then you would have an interval of convergence and that would look something like you would have the absolute value of x minus a would be less than some numbers, for instance, and then you could break out of this if you wanted to actually get the interval, and you would have a minus c, or x is between a minus c and a plus c. And then in this situation then, as long as x were between these two numbers, you would have convergence in the power series. And either one of these, c, if the c is infinite, if it's infinite in this direction or infinite in this direction or in both directions, then you have an infinite size interval for where it'll work on. Especially negative infinity to infinity, you've studied all sorts of power series that have that kind of an interval of convergence. E to the x is a perfect example. Cosine of x, sine of x, all those are perfect examples of those with infinite intervals. Other ones, like tangent and things of that nature, will not. So we're going to work on some arithmetic with these things. Probably the first thing I would like to tell you about is if I have a power series, say it's called a sub k x to the k, and I add to it another one, k equals a 0 to infinity, b sub k x to the k, then I can add them up term by term because the x to the k's are of the same power. You can add like terms, assuming this is for where it converges, of course, and that's usually what we will consider, is where these things actually do converge. So I could add together the a k and the b k, and those be taken to the xk power. Works for subtraction as well. Dummy variables, you should know that I can write k equals 0 to infinity a sub k x to the k, and that would be no different than if I had written n equals 0 to infinity a sub n x to the n. That's no different if I had written something besides any of those letters. Sometimes some authors I've seen even use Greek letters, like mu from 0 to infinity a sub nu x to the nu. So all these are the same thing. It does not matter what this letter here is called the index. It does not matter what letter you use for the index. Additionally, we refer to 0 and infinity as the limits of summation. Now, let's get started with doing some derivatives and whatnot. Suppose I have a function, f of x equals the summation k equals 0 to infinity a sub k x to the k. Now, if you wrote it out in longhand, you would have a sub 0 x to the 0 plus a sub 1 x to the 1 plus a sub 2x squared plus a sub 3x cubed plus a sub 4x to the 4th, and that goes on forever. Now, if I take its derivative, if you differentiate like you would, this is just a very long polynomial. X to the 0 is equal to 1, so that was just a 0 there. So the derivative of a constant is 0, of course, and we end up with just a1 plus 2a2x plus 3a3x squared plus 4a4x cubed, and go on forever. Now, if I try to rewrite this as a series, notice now it starts at 1 and instead of 0. Let me pull that down a little bit so we can compare. This series starts at 1, whereas the original series started at 0. So it would be good for me to write k equals 1 to infinity. But then I would want to go a sub k. And if I try to do this, let's try, first of all, this little thing here is causing some problems as well. I'll deal with that in just a second. Let me make sure I get my powers right. If I try to write this, when I start, you'll get a1 is matched with x to the 1, and that's not true. X to the 1 is matched with 2a2. So how can I match these correctly? Well, probably the better thing to do is to put a minus 1 here, right? And that way, when k is 1, I have a sub 1 x to the 0, and x to the 0 will be taken as 1. And so I have that part, but now I did not do the part, these coefficients. And if you'll notice, if I throw a k in front of here, then when k is 1, I have 1 times a sub 1 x to the 0. That matches a sub 1. When k is 2, I have 2 a sub 2 x to the 1. 2 a sub 2 x to the 1. 3a sub 3x squared. See if you can follow the k's. The point that I'm making is this. When I started with the original, k equals 0 to infinity a sub k x to the k, you can hope and pray that when you take the derivative, you should be able to take the derivative of each and every component. So instead of just like you would a polynomial, except it's an infinite polynomial. So you hope that the rule that you use for differentiation is you bring the k down and you subtract 1 from the power. Like so. So this would be the derivative of each individual piece. Now, you got to know, though, that you start this time is when k equals 1 and go off to infinity. That's not always going to be the case, but a lot of the times it is the case. Notice that in the original function I start at 0. In the differentiated function I start at 1. So when they're simple polynomials like this, even though they're infinite, they will work like this. As an example, I wanted to remind you of perhaps the most important of all power series, and it looks like this. Summation k equals 0 to infinity x to the k. This is called the geometric series, because it's so important. And there's a lot of geometric series, but this is the one that they're all based on. Now, this is true whenever x is between -1 and 1. So, in fact, the open interval from -1 to 1 is the interval of convergence. And in calculus, it was quite useful to be able to take derivatives of this thing. In fact, let me take the derivative of both sides. All right, let's start with the derivative of the left-hand side. I was going to be tricky, but I think I'm just going to use the quotient rule for the left-hand side. I'll get 0 times 1 minus x minus 1 times negative 1 all over 1 minus x, that quantity squared. On the right-hand side, we can take the derivative term by term, and when k equals 0, x to the 0 is going to be 1, so my first term is a constant. That means I can write this as k equals 1 to infinity, k x to the k minus 1. So you were able to, once you had the original series here, you can differentiate and integrate to your heart's content to get new series. Over here, all this stuff simplifies to 1 over 1 minus x, that quantity squared, and that's equal to k equals 1 to infinity, k x to the k minus 1. So it works just like we want. The k starts at 1 now. Now, as I mentioned, that is not always true. Let's take a look at another one. You'll recall probably that sine of x is equal to the series k equals 0 to infinity. And here, this was a little more complicated. X to the 2k plus 1 all over 2k plus 1 factorial. Let's take the derivative of both sides. And now what I'm going to try to do is do term by term on the right. The left-hand side we know is cosine of x. So can we get a series for the sine of x? Well, if you try to do this, start it at 1, then we're going to have 2k plus 1 x to the 2k, since you subtract 1 from the exponent, all over 2k plus 1 factorial. You might have known that you can cancel out the 2k plus 1 with this 2k plus 1 and end up with the summation k equals 1 to infinity x to the 2k. This goes 2k plus 1, then 2k, then 2k minus 1, all the way down until you get to 1. So if I cancel out the 2k plus 1, I'll simply have 2k factorial. Now, if you write this out, you'll end up, when k equals 1, you'll have x squared all over, when k equals only 2 factorial. And then, oops, I made a mistake. Let me fix it while I'm here. There actually is a negative 1 to the k in front of here. So I'll keep putting it in. I may have to fix it here. Negative 1 to the k. There we are. Negative 1 to the k. That way, I made a mistake here. That way, when k equals 1, this is a negative number. And then we'll have x to the 4th all over 4 factorial. In fact, the 2k is always going to be an even number, just like the 2k plus 1 was always an odd number. And this will alternate in sign. Now, the problem with it is that cosine is not equal to this. So, in fact, this is not equal. The cosine series looks like this. That series starts when k equals 0 and goes off to infinity, negative 1 to the k, x to the 2k, all over 2k factorial. It is this series, except for this series is missing the leading term. So what happened? Why couldn't I start at a 1? Well, it all has to do with the first term of sine is not constant. So let me do this again. This time, let me write out some terms. We have negative 1 to the k, x to the 2k plus 1 all over 2k plus 1 factorial. Those 2k plus 1s will guarantee only odd powers of x will appear. In fact, sine of x is an odd function, so that kind of goes hand in hand. When k equals 0, negative 1 to the 0 is equal to 1. So what this actually equals is x minus x to the third over 3 factorial plus x to the fifth all over 5 factorial minus x to the 7th over 7 factorial plus dot, dot, dot. So then cosine of x, if I differentiate this, I'll get a 1 in the first spot minus, now you'll get 3x squared over 3 factorial. Now I get plus 5x to the fourth over 4 factorial minus 7x to the sixth all over 7 factorial. And that goes on and on. Now, the 3 that's in front of here will cancel with the 3 that is out front of this factorial, and I'll get x squared over 2 factorial plus x to the fourth. I made another mistake right there. That's a 5 factorial. But after you cancel out the 5s, you'll get your 4 factorial minus x to the 6th over 6 factorial. So you can see that what I wrote up here is actually the proper way to write this series. So what happened? The problem with sine is it did not start with a constant. That first term is not constant. So all I can say about what you're doing as far as the index is concerned, where it starts, be careful. You do not know for certain that the first term will be erased by differentiation. That's why if I had done this correctly to begin with, you would make note that the first term here is equal to x. And then I can correct this by going back and putting my 0 in here. And then I can fix these not equal to's. And that'll fix everything. All right, I'm not going to dwell a lot on this, but I am going to be taking derivatives term by term like I have been doing here and showing you how it leads to series solutions. Let's start with a really easy series and see how you actually solve the differential equations with them. So let's start out by solving 4y prime plus y equals 0. This is an incredibly easy thing to solve with our normal methods. In fact, you can just swap the y over there, integrate, and you're done. This is a, what do they call that? It's so easy, separable function. It's so simple. Or you could divide by 4 and work the integrating factor. But anyways, what we're going to do is we will set y equal to the summation k equals 0 to infinity a sub k x to the k. The idea is we're going to figure out what all of the AKs are, and therefore we will know y. So it is important then to be able to differentiate and plug it into this equation. So let's go ahead. Y prime will equal, and I will do, this does start as the first term is a constant. It's a sub 0 x to the 0. A sub 0 is a constant. So I can start this at 1. And I'll get k a sub k x to the k minus 1. Now let's plug it into the differential equation. 4y prime plus y equals 0. Let me go and replace y prime with this stuff. So I will get 4 times the summation k equals 1 to infinity k a sub k x to the k minus 1 plus, and then y was equal to k equals 0 to infinity a sub k x to the k. And that equals 0. The 0 on the other side I do not want to worry about for a while. Next, I will suck the 4 inside of here. So k equals 1 to infinity 4k a sub k x to the k minus 1 plus the summation k equals 0 to infinity a sub k x to the k equals 0. Now, the weird thing here is the powers appear to be different between the two of them. How do I remedy that? How do I fix it so that I have an x to the k that I can combine with an x to the k? How do I get like terms out of the deal? Well, what you do is this little trick. Let me let u equal k minus 1, just like you would do anywhere else. Except I don't have to do a du or anything like that. I can just plug it in here. So when k equals 1, u will equal 0. And then when k equals infinity, well, u will equal infinity. Infinity minus 1, still infinity. So when u will equal 0 here to infinity, but then I'll get 4 times u plus 1 times a sub u plus 1 x to the u plus the summation k equals 0 to infinity a sub k x to the k, and that's equal to 0. Now I'm going to appeal to the fact that this u is a dummy variable, and I'm actually going to switch back to k. Because the variable is dumb, it doesn't know. So I'm going to say k equals 0 to infinity, 4 times k plus 1, a to the k plus 1, x to the k, plus the summation k equals 0 to infinity, a sub k x to the k. Now they're perfectly amenable to be added together because they have like terms of x to the k. So I can rewrite the left side as the summation k equals 0 to infinity, and then I'll have my x to the k that I'll have common to these, but what we'll also have is 4 times k plus 1, a sub k plus 1, plus a sub k. All of that will be times x to the k. And now this, believe it or not, will lead to our series solutions, this stuff right here. If you look, if I were to write this out, I would have a bunch of stuff times x to the 0, then a bunch of stuff times x to the 1, then a bunch of stuff times x to the 2. Well, 0 is no different than 0 plus 0x plus 0x squared plus 0x cubed forever. This is kind of like the same as being able to write a decimal with an infinite number of zeros after it. So what that tells me, if you match coefficients, for every single version of k, each of these will equal 0. So what I'll get is this will always be equal to 0. And in fact then, what I'll have is 4 times k plus 1, a sub k plus 1, plus a sub k equals 0. Now I'm going to leave the a sub k plus 1 on the left and get the other stuff to the right. So I'll get a sub k plus 1 will equal negative a sub k all over 4 times k plus 1. And this is how we start to generate our solutions. What I'll do is base everything off of a sub 0. So using this, a sub 1, when k equals 0, will equal negative a sub 0 all over 4 times 0 plus 1 will equal negative a sub 0 over 4. A sub 2, using the same formula over here, a sub 2 should equal negative a sub 1 all over 4 times 1 plus 1. That's negative a1 over 8. But a1 equals negative a0 over 4. The double negatives will cancel, and I'll get a sub 0 over 32. So I got a sub 2 in terms of a0. I'm going to give myself a little more room. A sub 3, using this formula again, will be negative a sub 2 all over 4 times 2 plus 1. So that's negative a2 over 12. And a2 was equal to a0 over 32. And that will equal negative a sub 0 all over, well, 12 times 32, that's 384. And this goes on forever. So when we look at our y, let me keep this here. The y that was supposed to be our answer is a sub 0 plus a1x plus a2x squared plus a3x cubed plus dot, dot, dot. I can now replace, I'm going to stop right there, a sub 1 with negative 1/4 a sub 0. And then a sub 2 I can replace with 1 over 32 a sub 0. And then a sub 3 I can replace with negative a sub 0 over 384. But let me factor the a sub 0 out of everything. I may ask for more terms, possibly, maybe not. It depends. You can come up with a formula if you want. I will not bother with trying to actually get a summation formula, although a lot of books do spend a lot of time, a lot more time than I think personally, trying to find a formula for this summation. I don't think there's any reason to do that, and I don't require it. Notice here that the only thing we don't know is a sub 0. A sub 0 works as our constant in these problems. And you should know, let me go back to the original problem, that when you're solving a differential equation of order 1, like this one here, when you're solving it of order 1, you'll get one constant. If the order was 2, you'd get two constants, and so on. So we know we should only have one constant, and indeed that is true. Right there it is, a sub 0. For a more robust example, let me use a series to solve 1 plus x y prime plus y equals 0. Everything is kind of a little bit light right now. I know you could divide by 1 plus x and do integrating factors, but I'm not going to do that. We're going to use a series. So you're going to do the same thing as you did before. Set y equal to an infinite series. And we're going to try to figure out all the a sub k values. And as before, a sub 0 will be the thing that we base everything off of. Let me plug everything into the differential equation. I'll get 1 plus x, but the y prime will be k equals 1 to infinity, k a sub k x to the k minus 1. But then y will be k equals 0 to infinity, a sub k x to the k, that's equals 0. This, more than anything, the purpose of this example is to show you what you do to try to get these series to be added together. Right now, they start at the wrong number and the power is different, but I'm not going to go and fix it just yet. I'm going to distribute the 1 plus x through, and here's what I'm going to get. When I multiply by the 1, I will get k equals 1 to infinity, k a sub k, x to the k minus 1. The next piece, then the x, k equals 1 to infinity, k a sub k, x to the k minus 1, plus the summation k equals 0 to infinity, a sub k, x to the k equals 0. Now, what we have here, if you look at the first series, when you plug in k equals 1, I'll start with x to the 0. This also starts with x to the 0. That means that I'm going to be able to re-index by starting my k at 0, and it'll be compatible with this thing. However, this one in the middle gives us some more work to do. So before I do just that, let me multiply the x in here. Keep in mind, we're assuming that we're working on the interval of convergence for the power series. So x is in whatever interval of convergence we need to solve this problem. Now notice what happens when I bring the x in here. I'll have x times x to the k minus 1. So that will become x to the k now. So anyways, right now this starts at x to the 1. So it's not compatible with this because it starts with x to the 0 here, and this also starts at x to the 0. I'm going to re-index the first one. So let's re-index it. That means I plan to start k at 0 instead of 1. That's okay. When k was equal to 1, I had 1, a sub 1, x to the 0. If I do this, I can get that back by changing the k to a k plus 1, my a sub k to an a sub k plus 1, and then I'll have an x to the k. And you'll see everything still works. When k equals 0, this piece right here is 1, which matches the k that was there before. This k plus 1 is 1, which matches the k that was 1 here. And then it starts with x to the 0. Now, this series is now perfectly compatible with this series because they have like terms. Now, do I want to quite get it put those together just yet? No, I actually don't. What I would prefer to do is now make them all three compatible with each other. The problem with making them all three compatible is that this starts at 0, this starts at 1, and this starts at 0. Well, I can fix that. I can release a term. I'm going to release the k equals 0 term. And when k equals 0, I'll have 1, a sub 1, x to the 0. So I'll have 0 plus 1, a sub 0 plus 1 times x to the 0 plus. And then the series will continue on from there. And so it starts at 1, x to the first power. Right here, this starts at the 1 power. And then this last guy, I'm also going to release. Release the k equals 0 term. Not x equals 0, that looks k equals 0 term. Release k equals 0 term. So I'll have plus, when k equals 0, a sub 0, x to the 0. Plus, I'll move this over a little bit. And that equals, of course, 0. Now, let me take my released terms and simplify them a little bit. So I'm going to have a sub 1 plus, and over here I have a sub 0. Now in here I'm going to start combining all of my terms. I'll have my k plus 1, a sub k plus 1, plus k, a sub k. I'm grabbing these here, k sub plus 1, a sub k plus 1, that's right there. Then k, a sub k, that's right there. And then I'll have plus a sub k. And of course, all of that made up the coefficient of x to the k. So you can see it's a little bit simpler now. You can even go a little bit further. And notice that I can factor an a sub k out from that piece, and I'll actually get this. K plus 1, a sub k plus 1, plus k plus 1, a sub k. As before, we note that this 0 is actually equal to 0 plus 0x plus 0x squared plus 0x cubed plus, and that will go on. What that means is that 0 is the constant term. So this right here equals 0. And every single coefficient on x is also 0. So let me set a1 plus a sub 0 equals 0, and then I'll get a sub 1 equals negative a sub 0. From then on, for the rest of the terms here, careful, I just noticed a mistake that I made. Fix that. Now here then, we're going to have k plus 1, a sub k plus 1 equals the negative of that, negative k plus 1, a sub k. Well, this is really nice. Let me cancel those, and we simply have a sub k plus 1 equals negative a sub k. So let's take a look then. If a1 equals a0, then over here, let's follow this. A sub 2 equals negative a sub 1. But if you replace a sub 1 with negative a sub 0, that equals a sub 0. A sub 3 equals negative a sub 2. But we now know that a sub 2 equals a sub 0, so negative a sub 0. A sub 4 equals negative a sub 3, which will equal positive a sub 0. You can see the game that's being played here then. Our y, which equals summation k equals 0 to infinity, a sub k, x to the k. That, of course, is a0 plus a1x plus a2x squared plus a3x cubed, a4x to the fourth. Well, that's nothing more than a0 minus a0x plus a0x squared minus a0x cubed. I just want to make sure I got my coefficients right. Yep, minus goes on the third. Plus a0x to the fourth minus dot dot dot. That'll be a sub 0 times 1 minus x plus x squared minus x cubed plus x to the fourth minus dot dot dot. So there is your answer for y. Now, I thought you might find this interesting. Let me just do a note. This is not crucial, but here's a note. If you look at the series, 1 over 1 minus x equals the summation k equals 0 to infinity x to the k. If I wanted to make this into an alternating series like I have here, right now this is the same series except it's all pluses where this has alternating signs. I could instead replace x with negative x. So long if x is between negative 1 and 1, negative x is between negative 1 and 1. Well, then this, you can rewrite it as k equals 0 to infinity, negative 1 to the k, x to the k. And you can see that it's alternating. It's going to give you 1 minus, when k equals 0, you're going to get 1. When k equals 1, you're going to get negative x, etc., etc. So our answer that we got in that previous problem was that y equals a sub 0 over 1 plus x. I am not going to go through a lot of details, but this is just a note. This is fine for the answer. You do not have to do any of this, what I'm doing right now. What the written out answer is fine. But I just wanted to show you. Now, if I plug this into the original equation, which was 1 plus x, y prime, plus y equals 0, when I plug this in and take the derivative, I will get 1 plus x times, now when you take the derivative, I'll have a negative a sub 0, 1 plus x to the negative 2, plus 1 over 1 plus x, and a sub 0 over 1 plus x. That's supposedly what y equals. Notice then that I can cancel one of these and make that to the negative 1 power. And I'll get negative a sub 0 over 1 plus x plus a sub 0 over 1 plus x. And that, of course, does equal 0.